Pandemic modeling is an application of mathematical models used by epidemiologists to understand the behavior of a disease, as well as to acquire data. From the model, they could know how fast the epidemic will spread, the maximum number of infectives at a certain time, and how bad exactly is the situation. To get this data, epidemiologists use the SIR model. The SIR model divides the population into three groups. First is the susceptible. These are the people who could potentially acquire the disease. Second is the infectives. These are the people who already has the disease. And third are the remove. These are the people who have either already recovered from the disease or has passed away due to it. The SIR model has various assumptions. First is that it has a fixed population. That means that newborns, people who have immigrated, or death unrelated to the pandemic is not considered by the model. The second assumption is that the disease has no incubation period. That means that once you have become infected, you will immediately display symptoms and can infect other people. The third assumption of the model is that everyone is either equally susceptible or infective. That means that everyone has equal chances of getting the disease or infecting another person, no matter what your age, gender, social economic status, or current health conditions. The fourth assumption of the model is that the disease is transmitted via direct or indirect contact. Direct contact refers to direct skin contact, such as hugging, while indirect contact is touching an infected object. The fifth assumption of the model is that it has a large population. This is needed to have an accurate data and to avoid the chances of it being just random data. Let's talk about the formula for each category. First is the susceptible. The formula for its rate of change is ds over dt is equal to the negative the product of the transmission rate, the number of susceptibles, and infectives. This formula represents the change of susceptibles as time goes by. As you can see in the graph, there is a downward slope, indicating that the disease is spreading and the number of susceptibles is decreasing. This formula was formed with the knowledge we have that as time goes by, people become infected, thereby reducing the number of susceptibles, hence the negative sign. The next factor considered is the transmission rate, represented by the beta symbol, which is the product between the average number of contact a person has per day and the percentage or probability of getting the disease. The next factor is the contact between the susceptible and infectives, represented by their multiplied number, wherein the higher the contact, the higher the chances of the disease spreading. If put in an analogy, it will be like a rotten apple being placed in a basket of fresh apples, which will result in the fresh apple becoming rotten faster. Next is the formula for the actual value. The small letter n in the formula represents the day. Observe the formula and you will see the second term is just the rate of change, except the susceptible is in fractional form. So to get the number of susceptible today, you just have to get the difference between the susceptible yesterday and its rate of change. Next is the infectives. The formula for its rate of change is di over dt is equal to the difference of the product of the transmission rate, the number of susceptibles and infectives, and the product of the recovery rate and the number of infectives. As you can observe, the first term is similar to the formula of the susceptible. That is because all those who were infected were all just susceptible before. So now let's talk about the second term. So first is the recovery rate, which is expressed in time unit and represented as 1 over d, wherein d is the average number of days a person spent recovering from a disease. In other words, the second term represents the part of the infected population who have recovered or died. The usual graph of this equation is a hill-like shape, wherein the peak represents the maximum number of infected people at a day. Next is the formula for the actual value. As you can see, the second term is just the rate of change. So the number of infectives today is just the sum of the infectives yesterday and the rate of change. Next is the remove. The formula for its rate of change is dr over dt is equal to the product of the recovery rate and the number of infectives. As you can observe, it is similar to the second term of the infectives. That is because all who are in the remove were just those who were transferred out from the infectives. So the removed category includes two types of individual, those who have recovered and those who have passed away. And those who are in the removed category can't be transferred back to the susceptible. That is because the model assumes they become immune to the disease. And remember, the general trend of the graph of the removed is upward, meaning the number of removed grows as time passes by during an epidemic. Next is the formula for the actual value. So as you can observe, the second term of the formula is just the rate of change. So to get the removed today, you just have to get the sum of the removed yesterday and the rate of change. To understand it better, let's put it into an analogy. The analogy will be cooking mama's meat recipe wherein mama prepares the raw meat, cooks the meat, and serves the meat. So in this example, the population will be 10, for 10 is a large number to satisfy the assumption of the model. When mama starts to cook, the population will be separated into the susceptible raw meat and the infective meat. Remember the formula of the susceptible. The transmission rate in here is the rate in which mama transferred the raw meat into the pan. Wherein the faster it is, the higher the rate. Now the reason for the negative sign is because the raw meat decreases, because naturally you need to cook it to eat it. So for the infectives, formula. Let's talk about the recovery rate. In this analogy, the recovery rate will be compared to the cooking time, which is the amount of time the meat spends in the pan. An example would be a hot dog. If it needs 5 minutes to cook, then its rate will be 1/5, which would mean that 1/5 of the hot dogs being cooked will be available after. If it's a disease and you need 14 days to recover from it, then the rate will be 1/14, and which will indicate that 1/14 of the infected population will recover. So, the ones that's being deducted is the meat that has already been cooked. It will be transferred to the removed category, which is the served meat, which will therefore decrease the number of infectives. So, for the removed, which is the served meat, it only has two outcomes. Either it gets eaten or it becomes a leftover. Consider the ones who have been eaten as those who have passed away, and the leftovers as those who have recovered. And remember, a cooked meat can't become a raw meat anymore, just like how a removed person can't become a susceptible anymore. That's it for the analogy. Let us apply what we have learned. Imagine an island with a population of 123,456. Then a disease spread. The initial number of infectives is 5, and the transmission rate is 0.2, and the recovery rate is 0.05. To understand the pandemic, they decided to make an SIR model to know the spread of the disease. To make the model, they used these formulas. One for the susceptible, one for the infective, and the last is for the removed. And then, they made a table to organize the data they have. This data was used to construct a data table, which will be used to make the graph. So how was this made? Here's the solution. A1. First write the formula, then substitute the n to the number of the day. So all n will become 1. Solve. Then substitute it with the given. Solve again, and you will have the answer. So what about another day? Another example is day 9. So here's the solution. First, write the formula again. Then substitute 9 to the n, which is the number of the day. Solve. But this time we'll be substituting the day 8 of susceptibles and infectives. Substitute and solve, and then you'll get the answer for day 9. So to get the infectives and remove, you'll be using the same steps. Now doing this is tedious, so we can use the applications such as Excel to create our table of data and graph. Here is the graph of the example. The blue line is the susceptible, the orange line is the infective, and the gray line is the removed. In the x-axis, there lies the days. It is until 150. In the y-axis is the population, so it's until 140,000. Let's first discuss about the graph of the susceptible. At the start of the pandemic, the graph shows a minimal decline. This indicates that the spread of the disease is low, but at around day 40, it experiences a sudden decline. This indicates that at this period of time, the disease spreaded faster. From the graph, we could also observe that the line almost touches the x-axis. This indicates that the majority of the population got infected by the disease, which means that the situation is severe. Next is the graph of the infective. In the graph of the infective, we can know the maximum number of infected cases there are at a day when it reaches its peak. So in here, the peak is around 50,000 at day 80. So that means there's around 50,000 cases at that day. So after it reaches its peak, it slowly goes down until it's supposed to reach zero. And when it reaches zero, it means that the epidemic has ended. At day 150 in the graph here, it shows that it has not reached zero, which means the epidemic has not ended. Last graph is the remove graph. So in here, you could see the number of people who has recovered or died at that day. So in here, you could see that there's a sudden increase. This means that at this certain point of time, a lot of people has recovered. Graph. That's all. Thank you for listening.